Well, it's taken me a little bit, but we're ready to use this combination, linear combination, that is technique, to sneak up on and solve for the principal unit normal vector. I've given you a three-dimensional position vector, square root of 2 multiplied by t, 1/2 e to the 2t, e to the negative t are the three components. And we're going to actually, instead of just calculating the general principal unit normal vector, we're going to just do the calculation at a particular time 0. And this will be very much faster than if we had to algebraically use the definition. So let's just remind ourselves what we're talking about here. We're looking to find this, and supposedly we can find all of the other pieces to do so. Acceleration, this scalar, the unit tangent vector, and this scalar, and thereby sneaking up on this. I've also given you, without explanation, the unit tangent vector scalar, velocity, dot product, acceleration over magnitude of velocity, and this scalar that goes with the normal vector, acceleration's magnitude squared minus this constant squared, all in the root. So let me just show you how little calculus you have to do and how much arithmetic there will be, since we're only going to do the calculation at a time 0. So I'll come back and I'll show these details because we will need them. Alright, so here we go. First things first. Before you find acceleration, you have to find the velocity vector, and we need the velocity vector for several pieces that are hiding under here. So that's just the first derivative, and that would be square root of t, square root of 2 multiplied by t. The derivative is square root of 2, and the derivative of this is 1/2 e to the 2t multiplied by 2. And the derivative of this is e to the negative t multiplied by negative 1. The acceleration vector would be just the derivative of what we just found here. You know, the 2's reduce. Sometimes that's called canceling. And so acceleration is, well, let's see, what is the derivative of a constant? Well, that's 0. And what's the derivative of this? It's e to the 2t multiplied by 2 again, because this set of constants already reduced. And if this is negative, e to the negative t, and you take a derivative again, you're going to get a positive e to the negative t. We are finished with the calculus. The calculus is finished in this particular problem. We will need to know, what do we get if we substitute 0 into each of these. So let's do that. Velocity at time 0 is root 2, e to the 0 power is 1, and this will be negative 1. I believe we need the magnitude of the velocity vector in one of those numerous formulas. This is where you'd pause and you could go back and peek again, right? The magnitude of that will be, when you square this, you'll get 2, and you'll get 1, and you'll get 1. That's the square root of 4, which is, hey, that's 2. It may never be a nice number again. It might be a root, a radical value. What's the acceleration vector when time is 0? Let's see here. Well, the first is 0. That's going to be 2, and that's going to be 1. And I think you will find that we also need the magnitude of acceleration in one of these little problems. And the magnitude of acceleration is going to be 0, 2 squared is 4, plus 1, square root of 5. I claim we have finished our shopping trip to the hardware store. We have all the tools and parts we need to build this beast. But now I need to show you how to then apply the pieces. So let's let these other formulas come back into view. First things first, the scalar that goes with the tangent vector, I need to do the dot product of two vectors divided by a magnitude. Well, the dot product of the two vectors would be root 2, 1, negative 1, dot product 0, 2, 1. They're right here. Okay, so that was the first vector, and that's the second vector. And divided by the magnitude of velocity, which is 2. See, root 2 times 0 is 0. 2 times 1 is 2. We get 0 plus 2. We get minus 1 over 2. That's going to be 1/2. That's not horrible. And then the other constant, with respect to n, is, let's see, magnitude of acceleration squared minus a sub t squared in the root. Magnitude of acceleration squared, root 5 squared minus 1/2 squared. Let's see here. 5 minus 1/4. Oh, that's going to be the square root of 19/4, or root 19 divided by 2. Now, in order to write it in a way that it translates decently on a camera here, it's not the best way to present it to your instructor later. I've got pieces here, I've got my directions here, and I don't have room to combine them all together. If this were a test or exam or an assignment, this would fit on a piece of paper without too much difficulty at all. You'd be writing smaller than I am right now for certain. But let me just show you sort of where this is headed. Okay. So I'm trying to fill in these blanks. As many as I know. Remember, they're all calculated at time 0. I just was efficient and didn't write them here. Maybe that's being lazy. That's possible. Well, the acceleration vector was the vector 0, 2, 1. The scalar for the tangent component was 1/2. And hey, I don't know that I found the unit tangent vector. How do I do that? Well, that's velocity vector divided by its magnitude. I even wrote it so it's almost on the paper. Not quite, it's close. So that would be root 2 over 2, 1 over 2, and negative 1 over 2, plus the other scalar, which was not pretty, root 19 divided by 2. So I claim, in order to find that principal unit normal vector, solving this equation is a lot less work than doing it by the actual definition. And if you hadn't practiced with the definition before, you can go back to one of my earlier segments. It is a beast. And I did not give you nice algebra to play with at the beginning here. It's a beast, folks. So, let's do the solve. First, I'm going to distribute. 0, 2, 1, root 2 over 4, 1 over 4, negative 1 over 4, plus root 19 over 2 multiplied by our target, the principal unit normal vector. I'm going to subtract from both sides this vector. It's algebra, folks. Adding and subtracting vectors. You just add or subtract their matching coefficients, their matching components, excuse me. No problem. So 0 minus this value here is going to be first component negative root 2 divided by 4. 2 minus 1/4 will be 7/4, and 1 minus a negative 1/4 is going to be the same as adding 1/4, which would be 5/4, and that will be equal to root 19 divided by 2 multiplied by the unknown principal unit normal vector at t equals 0. We're so close. We're not necessarily excited. I'm excited about almost being finished, but I'm not excited about kind of the mess here. But you see, if you're one of the computer science majors in the room, this is a pretty simple little algorithm to get your computer to do. 2 derivatives and a whole bunch of numerical substitutions. No problem at all to make this computation, this little algorithm solve for a vector accurate to as many decimal places as you need. I'm going to solve for the normal vector. Instead of dividing by root 19 over 2, I'm going to write it as a multiplication. 2 over root 19. Root 2 over 4. 7 over 4. And 5 over 4. And when you multiply through this scalar, the 2's are going to reduce with the 4's. You're going to get first component negative root 2 over 2 root 19, 7 over 2 root 19, and 5 over 2 root 19. Your principal unit normal vector, I claim. Oh my goodness, I'm off the paper here. You've probably been waiting on me. My apologies. Now, before I wrap it up, I have 2 things for you to try to do. 2 things to try to do. All right, ready? Your assignment. 1. Is this a unit vector? Question mark. It will be. It's not too difficult of a calculation. Try it. Try it. Second, is it truly normal to the curve? Is it really perpendicular to the tangent vector? Translation. Does this dot product equal 0? Try those 2 things. You don't need me to do that. I don't need to burn through some more time and paper here for the arithmetic. Make this happen just in case that is my exam question or your teacher's exam question if you're just visiting. I do like visitors. All right, folks. We're going to wrap up the normal vector for now, and I'm pretty sure you're going to be happy about that. Until next time.